Assalamualaikum warahmatullahi wabarakatuh dan salam sejahtera. Yang berbahagia, Profesor Dr. Muhammad Roslan bin Sulaiman, Naib Chancellor Universiti Putra Malaysia. Yang berbahagia, Profesor Teknologis Dr. Rosli bin Haji Abdullah, Dekan Fakulti Sains Komputer dan Teknologi Maklumat. Yang berbahagia, Profesor Dr. Abdul Azim bin Abdul Ghani yang akan menyampaikan syarahan inaugural pada pagi ini. Ahli-ahli pengurusan fakulti dan para penonton yang dihormati sekalian. Selamat datang diucapkan kepada semua yang menonton majlis syarahan inaugural oleh Profesor Dr. Abdul Azim bin Abdul Ghani. Untuk makluman semua, majlis syarahan inaugural ini diadakan secara dalam talian mengikut norma baharu dan dipancarkan secara langsung melalui Facebook UPM dan Facebook FSKTM. Tuan-puan dialu-alukan untuk menekan butang like dan share halaman-halaman Facebook tersebut. Seterusnya, bagi memohon keberkatan majlis pada hari ini, majlis mempersilakan Encik Abdul Muttalib Kamarudin untuk membacakan doa.
Assalamualaikum warahmatullahi taala wabarakatuh dan salam sejahtera. Al-Fatihah. A'udzubillahi minasyaitonirrajim. Bismillahirrahmanirrahim. Alhamdulillahirabbil alamin. Arrahmanirrahim. Maliki yaumiddin. Iyyaka na'budu wa iyyaka nasta'in. Ihdinas siratal mustaqim. Siratal ladzina an'amta 'alaihim khairil maghdubi 'alaihim waladdallin. Amin. Bismillahirrahmanirrahim. Alhamdulillahirabbil alamin. Wassalatu wassalamu ala asyrafil anbiya'i wal mursalin wa ala alihi wa sahbihi ajma'in. Ya Allah, ya Tuhan kami, hanya padamu sahaja kami panjangkan kesyukuran atas segala rahmat dan berkat-Mu. Bersempena dengan majlis syarahan inaugural oleh yang berbahagia Profesor Dr. Abdul Azim Abdul Ghani pada hari ini, kami memohon inayah dan taufik-Mu. Kurniakanlah kesejahteraan dan kebahagiaan kepada kami. Bukakanlah hati-hati kami, lapangkanlah dada kami supaya kami dapat mengisi ilmu dan pengetahuan yang berguna untuk agama, bangsa dan negara. Ya Allah, ya Rahman, ya Rahim. Kami memohon kepadamu agar Engkau memberkati majlis ini dengan limpah rahmat-Mu. Semoga segala usaha kami dalam menjayakan majlis ini mendapat keredaan dan hidayah-Mu. Ya Allah, ya Zal Jalali wal Ikram. Dan kami pohon perlindungan dengan Engkau dari melakukan keburukan. Ya Allah, kurniakanlah kepada kami kekayaan ilmu pengetahuan dan hiasilah diri kami dengan sifat lemah lembut, serta muliakanlah kami dengan ketakwaan dan indahkanlah diri kami dengan kesihatan. Bismillahirrahmanirrahim. La yadurru ma ismi syai'un fil ard wala fis sama' wa huwa samiun alim. Allahumma inna na'udzubika minal basari wal junun wal juzam wa min sayyi'il asqam. Ya Allah, kami berlindung denganmu daripada penyakit sopak, penyakit gila, penyakit kusta dan daripada segala penyakit yang berbahaya. Rabbana atina fid dunya hasanah wa fil akhirati hasanah wa qina azabannar. Wa sallallahu ala sayyidina Muhammad wa ala alihi wa sahbihi ajma'in. Walhamdulillahi rabbil alamin.
Majlis merakamkan ucapan terima kasih di atas doa itu tadi. Para penonton yang dihormati sekalian, majlis dengan segala hormatnya mempersilakan yang berbahagia Profesor Dr. Muhammad Roslan bin Sulaiman untuk mempengerusikan majlis syarahan ini dan seterusnya menjemput yang berbahagia Profesor Dr. Abdul Azim bin Abdul Ghani untuk menyampaikan syarahan beliau. Majlis dengan segala hormatnya mempersilakan.
Terima kasih saudara pengacara majlis. Assalamualaikum warahmatullahi wabarakatuh dan selamat pagi. Yang berbahagia Profesor Dr. Rosli bin Haji Abdullah, Dekan Fakulti Sains Komputer dan Teknologi Maklumat, Universiti Putra Malaysia. Yang berbahagia Profesor Dr. Abdul Azim bin Abdul Ghani yang akan menyampaikan syarahan beliau pada pagi ini. Pegawai-pegawai kanan Universiti Putra Malaysia, ahli pengurusan fakulti, tetamu-tetamu jemputan, rakan industri, para staf dan pelajar, sidang penonton yang dikasihi sekalian. Alhamdulillah, syukur kehadrat Allah SWT kerana limpah dan kurnianya kita masih lagi diberi peluang untuk bersama-sama bagi meneruskan usaha memartabatkan kesarjanaan ilmu pada pagi yang mulia ini. Izinkan saya untuk membaca latar belakang Profesor Dr. Abdul Azim bin Abdul Ghani dalam majlis yang gemilang ini. Abdul Azim bin Abdul Ghani dilahirkan di Pasir Mas, Kelantan pada tahun 1961. Beliau menerima pendidikan awal di Sekolah Rendah Pasir Mas, Kelantan dan pendidikan menengah di Sekolah Tengku Abdul Rahman, Star, Ipoh, Perak. Setelah tamat belajar pendidikan menengah, beliau telah ditawarkan beasiswa MARA untuk menyambung pengajian ke peringkat ijazah bachelor dan telah memperolehi ijazah Bachelor Science dalam Matematik Sains Komputer daripada Indiana State University, United States pada tahun 1984. Pihak MARA telah menyambung beasiswa kepada beliau untuk ke peringkat kelayakan Master Science dalam Sains Komputer di University of Miami, Florida. Seterusnya, dalam tahun 1989, beliau telah menerima beasiswa SLAB untuk menyambung pengajian ke peringkat PhD dalam kejuruteraan perisian di University of Strathclyde, Glasgow, Scotland dan telah berjaya menerima ijazah tersebut pada tahun 1993. Abdul Azim menyertai UPM sebagai pensyarah di Jabatan Matematik, Fakulti Sains dan Pengajian Alam Sekitar pada tahun 1985. Selepas itu, beliau menyertai Jabatan Sains Komputer apabila jabatan tersebut diwujudkan pada tahun 1992. Pada tahun 1998, apabila fakulti baru dikenali sebagai Fakulti Sains Komputer dan Teknologi Maklumat dibentuk, beliau menyertai Jabatan Sistem Maklumat yang sekarang ini dikenali sebagai Jabatan Kejuruteraan Perisian dan Sistem Maklumat di fakulti baharu tersebut. Beliau telah menjawat jawatan Profesor Madya pada tahun 2001 dan jawatan Profesor pada tahun 2010. Abdul Azim merupakan Dekan Pengasas Fakulti Sains Komputer dan Teknologi Maklumat, UPM, dan telah memegang jawatan tersebut daripada tahun 1998 sehinggalah 2010. Sebelum ini, beliau juga telah memegang jawatan Timbalan Pengarah Pusat Komputer UPM, iaitu daripada tahun 1996 sehingga 1997 dan sebagai Pengarah Pusat Komputer UPM dari tahun 1997 hingga 1998. Beliau juga telah berkhidmat dalam pelbagai jawatankuasa di UPM sebagai Senat UPM, Jawatankuasa Kurikulum Universiti, Jawatankuasa Penyelidikan Universiti, Jawatankuasa Pemilih bagi Guru dan Profesor Madya, Jawatankuasa Semakan Senat, Jawatankuasa Beasiswa dan Cuti Belajar, Jawatankuasa Carian Dekan atau Timbalan Dekan, Jawatankuasa Audit dan pelbagai jawatankuasa di UPM. Abdul Azim telah menjalankan penyelidikan dalam bidang kejuruteraan perisian, terutamanya dalam bidang pengukuran perisian, kualiti perisian dan pengujian perisian. Beliau telah berjaya menyelia seramai 21 pelajar PhD, 20 pelajar master dan sebagai penyelia bersama seramai 32 pelajar PhD dan 18 pelajar master. Beliau juga telah menerbitkan sebanyak 155 artikel jurnal dan 140 artikel konferensi. Sekarang, marilah kita sama-sama mendengar syarahan inaugural oleh Profesor Abdul Azim bin Abdul Ghani yang bertajuk Software Measurement and Testing for Evaluating Software Quality. Sekian, terima kasih. Assalamualaikum warahmatullahi wabarakatuh.
Bismillahirrahmanirrahim. Alhamdulillahirabbil alamin. Wassalatu wassalamu ala asyrafil anbiya'i wal mursalin wa ala alihi wa sahbihi ajma'in. Assalamualaikum warahmatullahi taala wabarakatuh. Yang berbahagia Profesor Dr. Muhammad Roslan bin Sulaiman, Naib Chancellor Universiti Putra Malaysia. Yang berbahagia Profesor Dr. Rosli bin Abdullah, Dekan Fakulti Sains Komputer dan Teknologi Maklumat, Universiti Putra Malaysia. Yang berusaha Profesor Madya Dr. Hazura Zulzalil, Ketua Jabatan Kejuruteraan Perisian dan Sistem Maklumat, Fakulti Sains Komputer dan Teknologi Maklumat UPM. dan semua yang menonton syarahan ini secara atas talian. Pertama sekali saya ingin mengucapkan ribuan terima kasih kepada Yang Berbahagia Naib Chancellor yang sudi memperkongsikan majlis ini dan memperkenalkan saya. Terima kasih atas ketakluan yang diberikan. Yang saya muliakan Naib Chancellor dan semua hadirin. Izinkan saya memulakan syarahan saya dalam bahasa Inggeris. Ladies and gentlemen, today, computers play a primary role in almost every area of our life. Producing quality software is the ultimate goal of any software development project. Software measurement has been advocated as a key component in evaluating software quality. Meanwhile, software testing is the process of evaluating a software system with the purpose of finding out whether it meets the specified requirements. Software measurement, together with software testing, have played their respective roles in the evaluation of production of quality software. This lecture will encompass the research carried out by some members of the Software Engineering Research Group at UPM, together with myself and our student in the area of software measurement and software testing. Ladies and gentlemen, the content of this lecture are as follows. I will give a short overview on software measurement and software quality, followed by a topic on specifying metrics with attribute grammars, then the topics on improvement of the standard function point complexity weight system. The next topic will be component information flow metrics for component-based software system. Then the topics on structural metrics for business process execution language process models. And the last topic will be rambutans and automated test generation techniques for spec-oriented programs, and followed by final remarks and acknowledgement. First, let me start with the birth of software engineering fields. It is well known that while many software systems have been developed, some never delivered. Among those systems delivered may have been subject to budget overruns, late delivery, and lacks of quality. These issues are of great concern to computer experts and are referred to as the software crisis. Problems associated with software crisis relate to the characteristic of the software itself, which arise from the nature of the software. This characteristic play a role in the process of producing software. The nature of software brings out its complexity. Furthermore, the software system we choose to computerize are also complex. In response to the crisis, the North Atlantic Treaty Organization, NATO workshops, held in 1969 and in 1968, introduced the term software engineering to infer an engineering approach to the production of software, to produce quality software on time and within budget. Over the years, much progress has been made in software engineering. As a result, numerous techniques and methods are now available, which aim to improve the quality and productivity of software development, such as structured analysis, information hiding, stepwise refinement, structured design, object-oriented design, aspect-oriented paradigm, automated software tools, software measurement, and software testing. This lecture is designed to cover aspects of software quality, software measurement, and software testing. And software testing will be focused on aspect-oriented programs. As I mentioned just now, Producing quality software is the ultimate goal of software development project. So let me explain a little bit on software quality. In the physical world, quality refers to some characteristic that can be measured, such as length, size, and color. In the software engineering community, software quality is an important and critical measure of success, given the application of software in a wide, ever-increasing variety of areas. In the ISO IEC 9126 standard, so quality is defined as the totality of features and characteristics of software product that can bear on its ability to satisfy stated and implied needs. This definition stresses the importance of having some forms of characteristics to be measured to determine if the software fulfills its stated need. To understand and measure quality, researchers have often built models of how quality characteristics relate to one another. Conceptually, software quality comprises a composite of many characteristics, usually expressed in a model that portrays the composite characteristic and their relationships. A software quality model is the set of characteristics and the relationship between them that provide the basis for specifying quality requirements and evaluations. Models to evaluate the quality of software have been designed with a hierarchical structure, defining the factors, also known as characteristics, and subfactors or subcharacteristics, which metrics are then assigned to each subfactor for evaluation. These are examples of software quality models. One of the earlier models proposed was the McCall model, also known as factor criteria matrix. Another model is ISO 9126 model. This model was derived from McCall model and was an international standard for evaluating the quality of software. Subsequently, the ISO 9126 model was revised and ISO IEC 25010 model is established. Software engineering needs measurement in order to quantify aspects of software development and maintenance and the product produced. Measurement allows observation to be presented in numerical form and provide data which are used to make decisions, make inferences, and prediction. In the area of software engineering, the topic of software measurement has been discussed over many years. The increase in interest has been due to problems with resource estimation, attempts to quantify the quality of our products, and attempts to find a means of monitoring and controlling a project. Software measurement supports evaluation of software quality and is therefore an increasingly integral part of any software development process. Why we do software measurement? We perform software measurement is to understand, control, and improve the various quality attributes of the software and the underlying development and maintenance processes. Measurement for understanding is to assess the current situation in order to make aspects of the process and products more visible and provide better understanding about the relationship between software activities and its entities. This will also establish baselines that can help in setting up goals for the future. Measurement for controlling is to allow monitoring of software activities and its entities based on the established baselines, goals, and understanding of their relationships. The outcomes may be changes to the product and the processes in order to achieve the stated goal. Meanwhile, measurement for improvement is to improve the software activities and its entities. Measurement is defined as the process by which numbers or symbols are assigned to attributes or entities in the real world in such a way so as to describe them according to clearly defined rules. The definition is primarily concerned with capturing information about attributes of entities. In a software, there are three classes of entities of which attributes may be measured. First is processes. These are software-related activities that span over time intervals, such as design activities and testing activities. Second is products, which are any artifacts, deliverables, or documents produced by the process. Third is resources, which are the items required as input to the processes, such as designers, programmers, and software tools. The three entities mentioned just now have specific attributes. For example, process attributes include times, effort, and cost. Product attributes include size, complexity, cohesion, coupling, reliability, and so on. Resource attributes include productivity, experience, age of personnel, size of teams, and etc. Attributes of the entities can be divided into internal attributes and external attributes. An internal attribute is measured solely in terms of the entities themselves. For example, the size of a program is an internal attribute. It depends solely on the program concerned. On the other hand, an external attribute is measured based on how the entities behave within their environment. For example, the testability of a program depends on both the programs and the execution of the program in the environment used for testing. Measurement of the internal attributes is done because they are claimed to influence external attributes. During software development process, many intermediate and final software products are developed and measured using software metrics. These software metrics are classified as software products metrics. Under this classification, the metrics can be further categorized as source code metrics, design metrics, and specification metrics. The metric used to measure the software processes are known as software process metrics, and the metric used to measure software resources are called resource metrics. Let's look at source code metrics. This category of metrics focuses on measuring the source code. It is a very important component in software measurement process and is commonly employed to evaluate and improve the quality of source code itself. Various types of source code metrics for different programming paradigms have been proposed over the years. One of the earliest and perhaps the simplest metrics derived for source code is line of code, or LOC. This is the most common metrics of program size that is still widely used since it is easily calculated simply by counting the lines of code using very simple tool. Another well-known source code metric is called Halstead's metric or software science. It was an attempt to develop a comprehensive theory on the metrics for several attributes of a source code. The basic concerns of the metrics is the process of mental manipulation of selecting and arranging source code symbols to construct a source code. The symbol can be either operands or operators, and a program can be thought of as a sequence of operators and their associated operands. Unfortunately, for LOC, despite its simplicity, there are a number of variations of its definition in existence. For a specific piece of a source code, one may count the total number of lines as the source listing, including comments and blank lines. Or one may discard the comment and blank lines, and one may or may not count the declaration. The differences in interpreting lines of code and hence its definition depend on the manner in which the source code is modeled. Nevertheless, in a development environment, it is practical to have a consistent definition for counting LOC so that the metrics collected are comparable. In the case of hosted metrics, hosted did not precisely define which symbols should be treated as operators and which are operands, though he did provide a few examples. Thus, it is important that the counting strategy is clearly defined and consistent. Another metrics based for the source code metrics that is often mentioned is McCabe's metric or cyclomatic complexity. This metric was used to predict the effort of testing a software product. The metric is derived from a flow graph, a model of control flow structure of the source code. It measures the minimum number of basis paths in the flow graph or linearly independent path, which determine the complexity of the programs. However, as can be seen in the slides, two different control flow graph models can be generated if there is a compound conditions. The limitation is on how the mapping of the source code into control flow graph can be accomplished. In a study using static analyzers to get the metrics for the source code, it was found that two static analyzers produce two different values for the same metric for a given source code. Even though the analyzers were not wrong, the issue was that there was no precise way of mapping onto perspective model as mentioned above. The value of metrics are likely to be of limited use unless they are repeatable and comparable. Thus, it is necessary for software metrics to be rigorously defined and unambiguous. The next category is design metrics. Design metrics are metrics that can provide early information about a product at a much earlier phase than the source code metrics. Early work on design metrics was centered around the structural aspect of the design that concern with the division of a system into modules and how the modules relate to each other. One of the earliest metrics under this category is the information flow complexity. Researchers model this metric by viewing a system in terms of modularization of the system design, that is the number of information flow passing through each module. This metric is calculated by identifying fan-in, fan-out, and the complexity of a module. Other design metrics are based on call graph. A call graph is obtained by representing modules as nodes and modules called as edges. A metric defined based on the call graph is called graph impurity. This metric determines how far the graph departs from a pure tree and thus claims to measure the complexity of the connection within the design. Other metrics that are based on the overall system structure are morphology, measures, and tree impurity. In addition to the above metrics, in evaluating the quality of software design, two concepts known as coupling and cohesion are also used. Coupling is the measure of the degree of interdependence between modules, and cohesion measures the degree to which the components of the module are functionally related. The benefit of design metrics in providing early information about development of software products are more evident in metrics derived from specification document. Metrics for this phase are concerned with requirements gathered from user. One of the earliest metrics proposed is the function point analysis. This metric is used to measure This metric is used to measure the software functionality derived from users' functional requirements. It is measured based on the number and complexity of various inputs, outputs, inquiries, and databases as determined in requirements document. The computation of function point is carried out in two steps. Firstly is the computation of unadjusted function point, UFP, and secondly is the computation of the technical complexity factor, TCF. Okay, the value of FP, then UFP multiplied by TCF. Nevertheless, the function point matrix has its limitation in terms of the definition of the features, subjective complexity rating, and the weighting factors that may not be suitable for most environments. Thus, researchers have proposed variation of function points matrix in order to overcome this limitation. Among the variations proposed are feature points, 3D function point, Mark II function point, full function point, cosmic full function points, and IFPUG version of function point. Another matrix derived from software specification is the bank matrix. Bank matrix are defined based on semi-formal specification notation, such as data flow diagrams, entity relationships diagrams, data dictionary, and state transition diagrams, derived from structured analysis and design method. Others, as inspired by function point, a more method proposed to calculate the size of software known as use case point, which is related to use case diagram and use case description. With the advancement of object-oriented paradigm, there was a move to develop a method similar to function point, but with the notion of objects in developing software. As an object in this paradigm encapsulates both data and behavior, the functional user requirements assumed by function point is not as readily determined when applying function point to the object-oriented model of requirements. One method proposed in object-oriented software development is the OO method function point. This method provides a mapping of the object-oriented conceptual model onto the function point analysis concept in accordance with a set of measurement rules. Object-oriented programming is another focus of the software engineering community in improving software development. Object-oriented programming exhibit different characteristics from procedural programming due to the different programming philosophies of the two paradigms. In object-oriented programming, the concept of inheritance, classes, and message passing are involved, where these concepts cannot be characterized by any of the metrics defined for procedural programming. Due to these differences, other types of software metrics have been defined for object-oriented paradigm. The metrics defined in the table are the pioneers in object-oriented metrics for measuring object-oriented code. The metrics cover the most important attributes of the object-oriented code, such as size, complexity, inheritance, coupling, and cohesion. Ladies and gentlemen, let us move to the first topic of my research. This is my first involvement in software measurement research in which to specify metrics with attribute grammar. The work on this topic was motivated by inconsistency in defining metrics for source code. In view of this issue of defining source code metrics, language syntax may be used to define source code metrics at several levels, such as at the lexical level, context-free level, and context-free syntax plus static semantic level. One approach was by adopting attribute grammars to specify source code metrics. Attribute grammars were first proposed by Knuth in 1968 and were used to formally specify programming languages. Since then, they have been adopted in many applications such as compiler construction, anomaly detection for programs, and as a basis for a language-based editor. The grammar consists of the syntax defined by a context-free grammar and static semantics defined in terms of attributes, which are inherited and synthesized attributes, augmented to the synthetic symbol, and semantic function which determine rule or rules specifying the relationship which must hold between the values of attributes appearing in the production. From the perspective of specifying source code metric using attribute grammar, it encompasses context-free means of specifying the language syntax and attributes plus semantic functions to define the calculation of the source code metrics. The metrics are specified in terms of source code itself. Attribute grammars have brought about a few advantages in specifying source code metrics. They are as follows. They are as powerful as Chomsky type 0 grammars and are often considered more readable since the context-free grammar on which attribute grammar are based is completely visible. They combine the language syntax and static semantic in a modular declarative fashions and in a manner from which the static semantic specifications can be readily implemented. And they have the capability of using techniques for producing efficient parsers directly from them. In this slide, the definition of Mackay's metric using attribute grammar is shown. The general idea is to obtain the number of linearly independent paths of each module in a piece of source code. Becker's norm form is used for the production of the context-free grammar, of the attribute grammar, with the appropriate attributes related to the metric calculations are augmented. The value of the matrix is obtained by counting the number of decisions plus 1. So in the grammar, attributes con 1, con 2, and con 3 are used to evaluate the matrix. The function Vg is the rule to add 1 to the number of decisions. And this figure shows an example of CAPE's metric calculation. The example shows a pass tree associated with the procedure given at the upper left of the figure. The idea of using attribute grammar in specifying metrics has also been adopted when specifying metrics for design artifacts and software process. First is the work to extract design metric using attribute grammar. This was accomplished by developing a context-free grammar for a design specification language representing design structure chart. Augmented to the context-free grammar are the attribute values used to calculate the design metrics. Another work was on integrating measurement in software process modeling with the aid of attribute grammar. The work used integrated definition for process capture, which is IDEF3 standard notation, to design the software process model. IDEF3 SPMA language, which is a context-free grammar, was proposed as enhancement of the IDEF3 language syntax. Attached to the grammar are attributes used to calculate the metrics, such as size of process structure, number of calling sub-processes, and number of single processes. The next topic is on improvement of the standard function point complexity weight system. The function point matrix that I have explained previously has its limitation in terms of the definition of the features, subjective complexity ratings, and weighting factors that may not be suitable for most environments. The classification of function types into simple, average, and complex only simplifies the adjustment. This classification does not reflect the entire complexity of the work, which is necessary to develop the user system. Function point suffers from weight weakness, where the choice of weights for calculating unadjusted function points were determined subjectively from IBM experience. Thus, a new weight system for the International Function Point User Group version of function point was suggested. This was to reduce the error rate of prediction degree and to increase the accuracy of function point measure. The idea was to produce a new weight system with an absolute scale instead of the original ordinal scale, and thereby reducing subjectivity in the weighting system. The new weight system was established using the artificial neural network methods to modify the complexity weights of the FPUG version of FP measures. This figure shows the layout of the creation process of the new weight system. The original weights were the starting point in the creation of the solution, which are used as the 5 rules tables. It includes many substages such as mathematical calculation, spatial algorithm and creation of training database and network learning, and the artificial neural network method algorithm is applied as a prediction rule, as a prediction tool. The steps taken in this method are as follows. First, close the output interval of function types rules table. The final interval of data elements, record elements, and file type reference in the function type rules tables are open. Thus, all these intervals must be closed. Second, select weight sample of function types. The interval centers of data element, file type, reference, and record element in each weight class are calculated. The calculated values, known as the main training pattern, are used for generating more patterns to learn and test the suggested neural network. The third step is normalization of training pattern. The objective of the normalization is to get values within the range -1 to 1 or from 0 to 1. The fourth step is the architecture of network use. The architecture of the network in this work consists of two inputs, many hidden nodes or neurons, and one output, which is the function point complexity weight. This network was created 5 times for the 5 function types of function point. This was because each function type has its own training data, which differ from one function types to another. And the last step is the outputs of the learned network. When the network has become ready, the new complexity weights of any pair of record element types and data element types can be produced directly as an output of this network. The network outputs can then be used directly for calculating the function point count. Evaluation of the proposed modification in the complexity weights was conducted by calculating the function point count and comparing them with the original weights. The real data set of software projects accumulated by the International Software Benchmarking Standard Groups were used. The accumulated historical project data included the development effort using the function point with all their data sets arranged properly for the comparison. Furthermore, in all cases, the total development effort or actual effort was given in working hours. The collected data of more than 205 projects were used in this research. The function point counts obtained from applying the new weights and the original weights were applied to the effort model. A scatter plot shown on the left of the slide is the linear relations between the actual and estimated effort using the original weight. The convergence between the two was not strong, where the R-square is 0.4829. The linear relation using the new weights is presented on the right of the slide. In this figure, the degree of convergence between the actual and the estimated effort is clearly seen to be higher, which is R-square equal to 0.7144. The results measured using the new weights were much better than that using the original weights when applied in the same function point version. The new weights increased the estimation accuracy of this measure. The new weight system produced much more accurate software effort values and also reduced the error rate in effort estimation in comparison to that of the original weight systems. Ladies and gentlemen, the next topic of my speech is component information flow metrics for component-based software system. Let us start with component-based software engineering. Component-based software engineering is characterized by the development of components for reuse and the development of component-based software systems that focus on assembling individual components that have been developed independently. Its aim is to reduce development costs and times and increase the quality of a software system. Component-based software development differs from procedural and object paradigms where the traditional software metrics and object-oriented metrics are unable to directly measure the quality of a component-based software system. In order to derive metrics for component-based software system, a generic model for component information flow is proposed, which shows the separation of the interface from the implementation, which is the core principle of component-based development. The figure depicts an interface perspective view. It focuses on what the interface must do without considering the detail about how implementation is accomplished. In the proposed model, two boundaries are considered. First, interface boundary, which separates the provider interface from a client. Second, body boundary, which separates the provider interface from its implementation. The feature flows in the component information flow are the inter-component flow and intra-component flow. The inter-component flow is determined when the provider interface communicates with a client to exchange information by inflow through a list of in parameters and outflow through a list of out parameters. For the intra-component flow, it is assumed that a data structure is used to store and retrieve the information needed by the provider interface, represented by the read flow and write flow. In other words, an intra-component flow takes place when an interface retrieves data from or updates the data structure. The next figure shows an example of the relationship between three components, A, B, and C. It is assumed that some of the functionality required by component A is implemented by C and B. The information flow among the components as a result of method calls and event firings represent the inter-component flow and the information flow inside the components to update or retrieve data from component store, the intra-component store. The information flow from A to B or from A to C is represented by a set of direct interflow plus a set of intraflows, whereas the information flow from B to C is represented by a set of indirect interflow plus a set of intraflows. Based on the concept of component information flow just now, two measures, namely component information flow complexity and component coupling, have been proposed to evaluate component-based software system as shown in this respective table. An experiment was conducted to analyze the ability of the component information flow-based metrics as indicators for changeability of the software component. Changeability is a sub-characteristic of maintainability in the ISO 9126 quality model. It indicates the quality of being capable of change. The change can be either at the component level, interface level, or operation level. The hypotheses were the component with a higher CIFC value of information flow will be more difficult to change, and component with higher CC value will be more difficult to change. The dependence variable was CIFC and CC matrix, while the dependence variable was the changeability of software component, which was measured by the time taken by participants to answer the questions related to component changeability and the participant ratings of difficulty of solution for the required change. The experimental object, consisting of 18 components designed with 12 changes for each component, were provided to 37 participants. The participants were required to modify the set of 12 changes for each provided component based on the component specification, collaboration interaction diagrams, and the complete architecture of the system. The time taken to modify each change was recorded by the participant. And finally, the participant rated the solution difficulty for each of the 12 changes. The data collected from the experiment were tested for anomaly, and it was found that the data were not normal. Thus, non-parametric Spearman correlation was thus used to test the hypothesis. So from the result shows that the null hypothesis was rejected and the alternative hypothesis was accepted. The empirical result provided evidence that the proposed metrics are useful changeability indicator. Ladies and gentlemen, next I will discuss on structural metrics for business process execution language process model. Business process execution language, or BPOL, is a popular web service composition language that has become popular among web-based organizations. BPOL is employed to create web services that are fully executable like any other software, and they are called processes. However, BPOL lacks the advanced modularity features found in other programming languages. And also, in BPOL, it is an inherent complexity and tend to grow even more complex with age as new activities are added to the existing process. High complexity may have undesirable effects on the BPOL process model, such as higher probability of error, poor understandability, and consequently, poor maintainability of the process model. The structure of BPOL process is similar to that of procedural language programs with a few exceptions. BPOL statements are called activities. Simple activities are called basic activities and are used for doing tasks such as assignments and invocations. Using the notational approach, a BPOL basic activity can be described as a node in a process graph, as shown in the figure. However, the same activity may require several lines of XML code. The control flow statements are called structured activities in BPOL, and most of them are similar to software control flow with a few exceptions. For instance, BPOL has two structured activities that can be used to execute parallel processing, which are flow activities and parallel activities. BPOL also defines a new type of branch activity, which is called the peak activity, in addition to the common if-else activity. The difference between two branches activity is that while the if-else activity tests a Boolean condition, the peak activity tests a message condition. Software programs and business processes have some differences, which mean that traditional software metrics cannot be applied directly to business processes. As a consequence of this, a suite of 7 new metrics has been derived from existing business process metrics or by adaptation of the software metrics. In this slide, the attribute measured from the people process are divided into 2 levels. Okay. In this slide are the process level metrics. They are length of process, information flow complexity process, cognitive complexity process, structural complexity of process, weighted structured activities and invoked in a process model. While in this slide are the structured activity level metrics, which are average length of structured activity and average cognitive complexity of structured activity. Experiments were conducted to analyze the ability of the 4 selected metrics, which are IFP, IF4BP, CCBP, SCBP, and WSAI, to predict the subcharacteristics of maintainability, which are understandability and modifiability. Understandability is defined as the ease with which a model can be understood, and modifiability is defined as the ease with which the model can be modified for possible errors, a specific modification request, or new requirements. In this experiment, correlation tests were performed to establish the significance of relationship, followed by regression tests to further establish the predicting ability of the selected matrix. 10 people process models of varying size and complexity were used. The tables show the process model and their matrix value and the summarized matrix values using measures of central tendency and measures of dispersion. The first experiment was hypothesized to investigate the relationship between the selected matrix and people model understandability. The dependence variables were the selected matrix, while the dependence variable was the understandability of a model, measured by the participant ranking based on the scale of difficulty. Since the data collected were not normal, non-parametric Spearman rule was used to test the hypothesis. Results of the correlation test indicate that all the metrics achieve significant correlation between the selected metrics and understandability at a 95% confidence level with all p-values below 0.05, as shown in the table. This led us to reject the null hypothesis and accept the alternative hypothesis. The negative coefficient shown in the table indicates that complexity and understandability have an inverse relationship. A regression analysis using quadratic regression was performed in order to determine if the selected metric can be predictor for understandability. The result listed in the table show that all 4 metrics that have R-square values with p-values that were below 0.05, thus rejecting the null hypothesis and accepting the alternative hypothesis. This means that the metrics can be useful predictors for understandability. Another experiment conducted was to investigate the relationship between the selected matrix and the Beeper model modification time and understanding time. The independence variable were the selected matrix, while the dependence variable were understanding time and modification time of a model. The dependence variable were measured by recording the time required to understand and the time required to modify each Beeper process model separately. Hypotheses were developed and tested relating the selected matrix with the model understanding time and modification time respectively. The participants were provided with a model each, together with the understanding and modification questions attached to the model. They were given a duration of 1 hour to complete the task. 2 data sets were extracted from the participants, which are mean understanding time and mean modification time for each model. The Spearman correlation coefficient was used to test the hypothesis. The results shown in the table show that the null hypothesis were rejected and the corresponding alternative hypothesis accepted. The result shows that whenever complexity increased, understanding and modification time also increased. Regression analysis using quadratic regression was also conducted to establish prediction ability of the matrix. The results of the regression analysis shows that all metrics except IF4BP attain significant p-values for understanding time. This means that this matrix can be good predictor for the understandability of Beeper process model. Further, the modification time result shows in the table indicate that only the SCBP metric passed the regression test with a p-value of 0.038, which is smaller than 0.05. Thus, the modification time null hypothesis was rejected and its corresponding hypothesis accepted. The modification time result also shows that the p-values of other metrics were all greater than 0.05. Hence, their null hypotheses were accepted. From this result, it can be concluded that SCBP is the only matrix that can serve as a good modifiability predictor. The last topic of my talk is on rambutans, an automated test generation technique for aspect-oriented programs. The focus of this topic is on testing aspect-oriented programs. Before we go into detail about the topic, let me introduce a little bit on software testing and object-oriented programming. Software testing is claimed to be an activity in which a program is executed with the intention of finding faults. The essence of software testing is to execute a program with a set of inputs and observe the actual output produced. The output produced is then compared with the expected output. This can determine if the tested programs contains faults. In other words, it is to determine the quality of a software system by analyzing the result from running it. The set of inputs used along with the corresponding expected output is called test case. Test cases are generated using testing techniques such as black box testing, and whiteboard testing. In recent years, several different types of technologies in various areas of programming paradigms have been emerged. Of this, aspect-oriented programming, or AOP, is one paradigm used in software development. AOP aims to improve the modularization by providing means of separating cross-cutting concerns, which are functionalities whose implementation cut across multiple modules, such as logging. On the ground that procedural and object-oriented programming are not sufficient to properly manage cross-cutting concerns, that resulting in code tangling and scattering that can reduce understanding and maintainability of the code. Thus, AOP was first introduced as an extension of object-oriented programming to handle this matter. Cross-cutting concerns are concerns whose implementation is scattered throughout the implementation of the rest of the system, in which they cut across and affect multiple modules in the system. A concern refers to anything, any engineering process is taken care of, and it could be a high-level requirement or a piece of specification, for instance. Authentication, login, resource pooling, and policy enforcement are some typical examples of cross-cutting concern in software development. Implementing cross-cutting concern in conventional programming paradigms result in code scattering, where instead of promoting modularity, the code is scattered to multiple modules. Code tangling is a result of single modules or methods implementing many concerns, where the code for implementing the concern is amalgamated. The modularization of cross-cutting concern in OP is achieved through a complementary set of programming mechanisms or constructs, such as point cut, intertypes, declaration, advice, and most importantly, aspect. Aspect, as the essential element of AOP, is a modular unit implementing a cross-cutting concern, which also accommodates the point cuts and advice. The given figure illustrates the concept of modularization of scattered implementation of cross-cutting concern using AOP. In the figure, the gray areas represent the scattered code, which have been modularized as an aspect after transformation, thus resulting in a separated aspect and base code. This slide shows example programs written in aspect J. Aspect J is an aspect-oriented extension of Java programming language. Aspect J extends Java by special construct called aspect, extension of standard Java class. It has methods and attributes, and it also contains two major aspect-oriented constructs, which is advice and point cut. Aspect can only be invoked at well-defined points in the execution of a program. These points are called join points. Example of join points are calling or execution of methods, access to an attribute, and initialization of an object. Join point can be determined in a point cut or point cut designator. A point cut describes a set of join points where an advice needs to be invoked. An advice is a method-like construct that contains code to be executed at a matched join point captured by associated point cut. Aspect J supports before, after, and around types of advice, which are executed before, after, and exactly at the join point. Since the AOP paradigm has new concepts and properties that extend the capabilities of other programming paradigms, testing of aspect-oriented software cannot be performed directly using the current testing techniques used for other programming paradigms. The new concepts and properties of aspect-oriented software poses new challenges and issues with regard to testing as listed in this slide. The issues listed have resulted in many researchers proposing new and extended techniques for testing aspect-oriented programs. Although the traditional testing techniques are applicable to a certain extent in testing core classes, they are not directly applicable in testing aspects. Rambutans, with its tool support based on Aspect J programs, is a rigorous automated test generation techniques that utilizes a random testing concept. The technique emphasizes on revealing AO-related faults and conflicts by generating tests to support testing of the major AOP mechanisms that are point cards and advice. The test data generated comprise random generation of join points in order to trigger advice and point cards in a random manner. Shown here is the conceptual design of rambutans. The technique creates test data incrementally for the aspect chosen for testing, in which the tests are constructed for a single aspect at a time. The technique consists of 4 major components shown in the green boxes, considered as its essential ingredients, which are the interface and a combination form the basis of rambutans. They are aspectual class extractor, cross-cutting dependency identifier, object creator, and object on and random parameter generator. In these slides are the algorithm. The bit RAMS algorithm takes as input the source code of a given aspect-oriented programs written in Aspect J and written as output the generated test data for aspect. Aspectual class extractor algorithm is a source file finder that extracts all Java and Aspect J source file in the Aspect J programs. In Aspect J, each aspect can associate one or more advice to one or more point cards. In turn, the association between a point card and the base code is a cross-cutting association represented by a dependency relationship. Cross-cutting dependency identifier algorithm recognizes the element that have been advised by the given aspect, generally all the advice join point, captured by the associated point card. The type of dependency considered in this component would be that of between aspect and classes. That's called cross-cutting dependency. Random number generator algorithm responsible for generating input parameters value by randomly choosing a value out of a set of all values for a given type. Meanwhile, the object creator algorithm responsible for constructing the new objects, generally the reference types. In this slide, the outline of layered architecture of rambutans. According to the architecture, the system takes expect J source code as input and generate a set of test data as output. Concerning the presentation layer, the input components reads in and verifies the expect J sources. The output components allow the user to view, save, or export the generated test to JUnit file. The rambutan's core module in the application layer implements the bit ramp algorithm and perform generating tests. Database layer contains database-related procedure and functionalities that can be invoked by the components in both application and presentation layer whenever is needed. An empirical study by means of mutation analysis was performed to compare rambutans and 4 existing automated AOP testing approaches, which are RAPS, Spectra, Respect, and EAT. For testing aspect in terms of fault detection effectiveness and test effort efficiency. Effectiveness is defined as the capability of each approach in finding faults. Meanwhile, efficiency is defined as the number of test cases required per execution time taken to produce test cases by each approach in finding these faults. In the experiment, 2 hypotheses concerning the effectiveness and efficiency of rambutans and the 4 approaches were tested. The independence variable was the testing approach, and the dependence variable was effectiveness and efficiency. In the experiment, 9 aspect J benchmark programs from considerably different application domains were used. The experimental design was a randomized block. Listed are all the measures collected in the experiment by each approach. The fault detection effectiveness was measured using mutation score matrix. This metric is based on the number of killed mutants in relation to the total number of mutants not being identical to the original program. For efficiency, the test effort in fault detection required by the testing approaches in the test cases per minute was measured. The experimental data collected were checked to determine whether they followed a normal distribution. Since the data were normal, a parametric test Anova without replication was used to investigate the hypothesis of the experiment. The effectiveness of the approaches in identifying faults in the selected AO programs was analyzed by comparing the ability of each testing approach in detection of mutants using their obtained mutation score. The mutation score reflects the fault detection ability of the testing approach as shown in the bar chart. The chart shows that rambutans had the highest mutation score for 5 out of 9 object programs. It could only obtain highest mutation score for 3 out of 9 programs, while Respect had the highest mutation score for only 1 out of 9 programs. The results show that rambutan performed better than the other 4 approaches in detecting fault, as it was able to detect higher percentage of mutants. The next chart shows the total average mutation score gained for all the object programs using different testing approaches. It can be clearly seen that rambutans had the highest average mutation score, with the remaining approaches having lower average score. Statistical tests using Parametric Anova were conducted to determine rejection or acceptance of null hypothesis. Using the experimental data, the randomized block ANOVA was calculated as shown in the table. As can be seen from the table, the null hypothesis for effectiveness was rejected, and consequently, the alternative hypothesis accepted. There is thus enough evidence to conclude that there are statistically significant differences in the fault detection effectiveness of rambutans compared to the other automated AOP testing approach. Next is on test effort evaluation. The test effort evaluation is another quality aspect that was investigated in association with efficiency evaluation of rambutans in comparison with other selected automated AOP testing approaches. The analysis was on the effort required by the approaches with respect to fault exposure. The analysis of the result was based on the two building blocks of test effort construction, which are the number of test cases and the execution time required to produce those test cases. The number of test cases produced by the approaches for each object program as recorded during the experiment is presented graphically in bar chart format as in the figure. The bar chart clearly shows that rambutan recorded the highest number of test cases required to detect and kill the reported number of mutants compared to the other approaches. The result also shows that rambutan not only detected the highest rate of mutants compared to other approaches, but also generated the highest number of test cases to do so. The execution time to produce test suites was analyzed by determining the execution time in minutes as elapsed time required for the generation of the corresponding number of test cases for all the automated testing approaches. The execution time taken to produce the test suite for each object programs recorded from the experiment is presented in the figure. The chart in the figure shows that rambutan required about 23.47 minutes to generate a total number of 520 test cases, whereas each respect, spectra, and RAPs required 33.03, 28.71, 25.64, and 23.71 minutes respectively to produce 509, 430, 435, and 444 test cases. It was observed that there is a functional relationship between the number of test cases and the execution time, in which the number of test cases run determines the time taken. Thus, it can be said that the more the number of test cases, the longer the execution time to produce the test cases. While rambutans recorded the highest number of test cases, it was shown to have the lowest execution time to produce the test cases. In this sense, rambutans might be seen as much faster than other approaches as it produced a larger number of test cases over a shorter durations. Additionally, this figure shows the result for the test effort efficiency measurement for the automated AOP testing approach. The figure shows that Rambutan had the capability of generating 22.50 test cases per minute on average, which was the highest compared to other approaches. Overall, the results indicate that Rambutan is more efficient than other approaches with less effort required. Statistical tests using Parametric Anova were conducted to demonstrate the difference in test effort efficiency between the testing approaches. This was to determine rejection or acceptance of null hypothesis with 1% significant level adopted. The result of the Anova test for test effort efficiency are presented in the table. As can be seen in the table, the results suggest rejecting the null hypothesis in favor of the alternative hypothesis at the 0.01 significant level. Consequently, the analysis led to the conclusion that there is a statistically significant difference in the test effort efficiency of rambutans in comparison to all other selected automated AOP testing approaches. Ladies and gentlemen, as a final remark to my speech, I would like to iterate that software engineering, one of major computing disciplines, concerned with engineering approach in the production of software. Software measurement and software testing are intended to elevate the quality of software delivered. Software metrics are capable to measure characteristics of software in relation to the quality attributes, while software testing has long been a source for validating the functionality of software. Lastly, I would like to take this opportunity to acknowledge people behind my career in UPM. First and foremost, my sincere thanks to the government of Malaysia for awarding me scholarships to pursue my higher education. I would like also to express my sincere gratitude to University Putra Malaysia for giving me the opportunity to be a part of this wonderful institution. Special thanks to the staff of the Faculty of Computer Science and Information Technology for all the support and assistance. I am grateful to the staff of the Department of Software Engineering and Information System and members of the software engineering groups at UPM for their understanding and cooperation. My utmost appreciation to all postgraduate students who have chosen me as a member of their supervisory committees. My heartfelt gratitude to my late parents, brothers and sisters. And also my heartfelt gratitude to my wife, my son and daughters for their love, understanding, always supporting my career and sharing the hardship and happiness. Finally, many thanks to all the people who have supported me in preparation of this speech, directly or indirectly. Okay, shown here are my ex-students who I am as the chairman. And this list of students that I was their committee member. And this is a list of my Master of Science students. I am as the chairman of their groups. And the last one is my Master of Science student. I am as the committee member of the studies. To all of you, may Allah bless all of you, all the best, good luck to all of you. Okay, with that, I would like to thank all of you. Assalamualaikum warahmatullahi taala wabarakatuh.
Para penonton yang dihormati sekalian, dengan ini maka berakhirlah sudah majlis syarahan inaugural pada hari ini. Sekali lagi, majlis merakamkan ucapan terima kasih di atas kesudian anda semua yang mengikuti secara dalam talian. Assalamualaikum warahmatullahi wabarakatuh dan salam sejahtera. #kita jaga kita.